in terms of what is actually happening over here, you would notice that there was one more problem that I implicitly solved without really thinking too much about it, right, which was the question of, I have two processors, let me call them P1 and P2, which operation should execute where, okay. I just chose to put A0 on P1, B0 on P2, and once I chose that, then it naturally makes sense to put C0 on P2, otherwise I won't meet my time constraint, okay. But for my next iteration, how should I do it? Should I continue with the same thing? Should I once again put A1 over here, B1 over here, C1 over here? And more importantly, if I go forward from there, what prevents me from doing A2 over here and then B2 and C2? And in fact, I could keep changing this, it need not even be in a periodic fashion. The problem with this is, it is not a periodic repetition of the basic schedule that I started with. In this case, it is fine, I clearly brought it out there only to show you that there could be a problem, it is clearly an artificial problem that I have created. So I would never actually do this, right. But in general, the question of which of the hardware resources should I execute a particular function on may not always be obvious, especially when you are trying to build an overlapped schedule, okay. So in terms of the terminology of what we are trying to solve, typically the problem is broken into a sequence of 3 steps that need to be solved, okay. There is a problem of allocation of resources. Then there is a question of binding, which takes a given operation and says on which hardware resource is this going to execute. And then comes the problem of scheduling, which talks about what are the exact time instants at which a given operation is going to execute. Going back to this particular problem, the allocation question would essentially be, how many processors and do I have the right kind of processors? Binding would then say A0 onto which processor, A1 to which processor, etc., right. Similarly, B0, B1, all of those, deciding which operation goes on to which processor, right. And the scheduling is actually deciding the time instance, which is pretty much what we wrote down earlier, right. When I drew the Gantt chart, it essentially means that I have completed my schedule. Now if you think about it, what you will realize is, what I drew in the earlier case was pretty much only the schedules. I implicitly sort of decided that I gave you 2 choices. The very first one was allocation of simply one resource, one processor, in which case everything has to happen sequentially. And the second more interesting case was where I have 2 processors and then I need to decide what goes where. But what if I had a situation where the processor that is available to me is capable of executing function type A but cannot execute B or C? An example of that is, let us say that A was an addition, whereas B and C were multiplication operations, okay. In which case I can do additions, I therefore need some other hardware that is capable of doing multiplication. In the case of the folding example that we looked at earlier, right, I always had to make sure that there was at least one adder and at least one multiplier. In other words, if I basically take my data flow graph that I want to execute, that I want to implement, right, the second order filter structure, and say I am only giving you one adder, maybe you might be able to go around implementing multiplication through repeated addition, but it is not easy. You need to have a lot of extra hardware to do that, right. You need to basically set up some kind of a loop, something which does repeated addition using a counter, multiplexer, registers, etc., and that is like totally different from just using a multiplier hardware, okay. Whereas if I give you only one multiplier, the multiplier can't add, so you simply won't be able to do the addition step at all, and you won't have enough resources to implement the data flow graph. So that is the allocation problem. How many resources should I allocate, okay. There are two ways of looking at it. One is what's the minimum that I need to allocate. The second is what if I allow a little bit extra, how will it improve the rest of my matrix. Okay. The binding problem is deciding what goes where, right, and scheduling is when it happens. And if you think closely about it, you will realize that at least binding and scheduling are very closely interrelated. And if you actually look at it, all three of these steps, allocation, binding and scheduling, are all closely interrelated, because how many resources I allocate to the problem determines the kind of schedule that I can come up with. Okay. And that in turn determines what kind of binding I can end up with for the final problem that I have. Okay. So, more terminology, there is specifically something that is called a static schedule, where everything, allocation, binding, scheduling, are determined at compile time. Okay. And this word compile time is something that I have used in the past and is something that you always need to keep in mind. There is a difference between compile time and run time. Compile time is when you are looking at the problem and deciding how to go about implementing it. You have time, you can basically spend a lot of time trying out different options and coming up with one particular architecture. But once you have done it, that's frozen. You cannot make any further changes in the architecture, and then you move on to the so-called runtime. And during runtime, the system is actually operational. It's taking inputs, it's executing and generating outputs. Okay. So, a fully static schedule is one where everything happens at compile time. Okay. This is sort of the ideal situation. Let us say that if I actually took hardware multipliers, registers, wired all of them together, took the output of an A to D converter and just fed it into that system, right, it can implement one particular type of filter, but that is it, nothing can be changed over there. That is a completely static architecture, a static schedule. Okay. What if I took the option of scheduling alone, right, and said that I will do the allocation and binding at compile time. In other words, which operation, how many hardware units are there and which operation is going to run on which piece of hardware, right, that I will specify at compile time. But the exact time instant at which they run, you can decide at runtime, right. Why would I want to do that? Let us go back and look at the very first, this diagram that we drew out here. How did I get this two processor schedule? I basically looked at my data flow graph, and the only constraint that I seem to be working with is the A0, B0, C0, those operations are going to execute on P1, A1, B1, C1 are going to execute on P2. The exact time instants need not have been specified, and in fact looks like they have not been specified, because basically what I did is I took A1 and executed it at the earliest time that it was ready, as well as there was hardware available for it. Okay. So, A0, B0, C0, A1, B1, C1, I have specified that they need to execute on the P1 and P2 processors respectively, but the exact time instants at which they operate are determined at runtime. This is something called a self-timed schedule or self-timed operation. The advantage of a self-timed schedule is I do not need to have this entire sequence of what happens when completely fixed at compile time. That is one advantage. But a bigger advantage is, what if a given function takes a variable amount of time? So, if there are variations in delay, right, how long a particular operation takes to execute on a given hardware, that can be very easily accepted by a self-timed schedule, because all that it is saying is, let the operation run, once it is done it will generate some kind of an indication, a flag or some variable will be set or something else will be there to indicate that this function is completed, and the next operation can then start based on that. All that I need to know is the sequence in which the operations need to happen. The exact time instants are not important. Okay. Implementing this in hardware is a bit more tricky. The previous one was very simple, I just need to have a counter and I can say at time 0 do this, at time 25 do this, at time 43 do this, right. At every time instant in the counter I know exactly what needs to be done. Self-timed is a bit more tricky. It basically says start this, wait for a done signal. Once the done signal has come, start this next operation. So the sequence of operations is given to you, what should be done next on this processor, but not at which time instant they execute, which means that that much extra overhead is required. There have to be those done signals, but it gives you that freedom. If there are operations that take a different amount of time to operate on different data, that can be very easily accommodated by this self-timed scheduling. Okay. There are then I can sort of extend this. Generally speaking, what we talk about for anything where anything more than the scheduling is left to be decided at runtime, we just call them dynamic. Okay. And there are two possibilities. One is dynamic binding and the other is dynamic allocation itself. Let us look at dynamic binding first. What this is saying is a given operation, I do not even know where it is going to execute at compile time. Can you think of an example where this actually happens in practice? Any multiprocessor system, right? So this laptop, for example, has more than one processor, right? And the operating system essentially takes care of deciding what operation goes on to which processor depending on what the available load is. Okay. So let us say right now there is absolutely no load running on this, right. I am basically writing something on the software over here, and all that the OS has to do is make sure that the display is working properly. But what if I start running a few different computationally intensive programs on this? The operating system then needs to decide at any given point in time which processor is free, bind the operation onto that processor and execute it. Okay. This is an oversimplification because in the case of the operating system, the operating system is also doing some time slicing, and it is actually sort of time multiplexing different things onto the same hardware. But in principle this is what is happening, the binding is happening at runtime. Okay. What about dynamic allocation? Because after all, on this system that I have over here, the number of processors is fixed, I can't change that. So does it even make sense to talk about dynamic allocation? Can you think of any such context where dynamic allocation might make sense? Not necessarily signal processing related, but any computation. If those of you who are familiar with the terminology in cloud computing these days, right, any kind of scaling that is happening at runtime, right. You look at Amazon Web Services, Google Cloud, what they say is, okay, you have a web server, right, you find that the load on it is increasing, they can dynamically scale. What that means is, if it turns out that your load on your system is going above a certain point, automatically there will be some other back-end system that is looking at the load on the different processors and can then decide, I have available a full data center, I will add one more processor to this. Okay. So even allocation in principle can be made dynamic, it can happen at runtime. Okay. Obviously the overheads associated with that are going to be huge, in the sense that it is not a trivial thing to do. Essentially there has to be something that can spin up a new system with the operating system image running on it, all the software has to be synchronized onto that, right. How do you make this efficient? Of course there is a lot of research that has gone on to it, but it is nowhere near as simple as saying, okay, the self-timed scheduling, just the time instant alone is going to be changed. Okay. But the point is, these three steps are sort of generally considered the three main operations involved in the process of scheduling, right. When we start looking at how we take the high level synthesis, that is the C code that you are writing, and start converting it into hardware, this is substantially what is going to happen, right. The compiler is going to look at the code that you have written and say, I need at least this many resources for this. This is how I am going to bind the resources on the operations onto the resources, and I need to come up with a schedule. Okay. For the most part, the synthesis over there is going to be static schedules, except when you are talking about having sort of communication between different such blocks, in which case that scheduling is likely to become dynamic and based on handshaking signals.